So this is just a quick teardown of a digital timer I purchased on Amazon. I've had it working for a couple of days now, and it hasn't had any bad problems with it, or it was pretty easy to program it. You could program it without instructions. Here's a small LCD display. It's kind of hard to see on camera, but you can see it better in real life. There, that's probably what it looks like in real life, and the angle straight on, it's hard to see on camera. So yeah, you have to program in your times and everything, and it just turns on and off all that at a certain time. And it is UL listed. There's a nice little label on there. As a timer switch. It's a Titan control. It's Apollo 7, 115 volts, 15 amps, 60 hertz, and 1,725 watts. It just had two Phillips screws in the back. And let's see if we can open it up, tear it apart now. It was really inexpensive, so I don't know if the build quality is going to be very good. Let's try to pry this thing apart. There we go. Quite a lot of tabs holding that together. And it says it does come with a backup battery, so it retains the timing and program memory after the power goes out or you unplug it. Which is quite nice, because it beats having to reprogram the timer every time the power goes out or you unplug it. Okay, well here's a little better view of the socket, I guess. So that just pulls right out. Yep. Looks like the ground and the white wire is wired right through, while the black wire is going to the control module. And there's also a low value resistor, around 100 something ohms, in that ballpark area. That's quite nice. It just slides right in this little plastic molding right there. That's quite nice. It's very rigid right there. So they're switching the live wire on there, and this insert just goes over for dust protection on the case. Yep, just a standard case. The plastic isn't the cheapest either. It doesn't feel like the ultimate cheapest plastic you could find, so that's nice. Looks like they saved some cost by not including these two screws right there. They just put two on these two corners right here. So that is pretty interesting. Let's dig further. Oh, these are pretty stubby little screws. No, self-tapping screws. Oh, that's very nice construction. Wow, it's really elegant. So it looks like we have the relays in this part and a big huge capacitor, mains rated capacitor, next rated, and what is that, a Is that the backup battery right there, or is that a... Oh yeah, that's a battery right there. Little tiny rechargeable 1.2 volt battery. Metal hydride, nickel metal hydride. Sorry. So there's that little tiny battery powering the circuit when it's out of the socket. There's a little transistor right there, probably powering the relay coil. There's a mains rated capacitor, 1 microfarad, X2, 250 volt. Yep, all the listings on it. Yeah, that's a good capacitor. $100 microfarad, 50 volts. What was that, did it say DJ on it? I don't know, I haven't seen that capacitor brand before for that small electrolytic. It's 105 degree rated though, so that's pretty good. And that transistor, let me take a closer look at it. It says HMPS, MPS, M42. It's very small writing. I'd never heard of that transistor before, but apparently it's switching the relay on and off, and you can see the they put out a cutout in the board. Let me take this off. Oh yeah, there's little plastic switches in there. Maybe hold the board in. What? How does that work? Does this whole module come out? Oh yeah, the whole module might just pop out. Oh wow, that's very nice. Hey, look at that. That's very interesting construction. They just got this whole module of the relay and everything in one little plastic enclosure, and then it just snaps right in. And let's look at the relay. It's a Illoway. It's hard to get with the lighting. It's our Underwriter Laboratories listed. 24 volts DC BE 24-1A-H-S. 16 amps, 240 volts. Or 16 amps, 125 volts, 50-60 hertz. So yeah, that's a mains rated relay. Let's see if we can find the maker on this battery. That is a trolley. See if you can zoom in on that a little more. Troily, Troily battery. Is it 800 milliamp hour or 80 milliamp hour? I think that's 80 milliamp hour. Little nickel metal hydride of 1.2 volts. That's quite nice. I like that. Just a tiny little backup battery for the circuit. And it was still running when I got it, so it lasts quite a while. Here's the pins going to the digital board. You can see it says SI, plus, minus, and C on it. Well, let's first see if we can just take off this plastic part on here to look at the underside of the circuit board. Might be something interesting on there, but it looks like it's all single-sided construction. Sorry. Okay, there it goes. That just wedged out. It was held on with a little clip. Okay, so here's the live wire. There's a nice little isolation slot in there. It's a little J. You put they undid the solder mask so they can have a little bit more current, since this does 15 amps. So that's quite nice. There's a little bit of flux residue on there still, but I don't think that would hurt anything. It's a little bit dusty from the residue. Might clean it up before I put it back in, just so it doesn't cause a problem in the future. There's also 4 holes for more isolation. Another slot right there for the creepage distance, and just another slot right there. That's quite nice. Okay, yeah, this just goes right under the relay contacts, and they just switch close. They just close these 2 points right here, and then it turns on the power. So that's very simple construction. Looks like it takes a tap off of here, and it gets half-wave bridge rectified with 2 diodes right there. And then this must be the smoothing capacitor. Is that a Zener diode right there? Is that a Zener diode? That's very interesting. Wonder what that diode is doing. Is that a Zener diode too? Let's look at the silk screen. There's no silk screen on the diodes, so I don't know if they're Zener or regular diodes. That's wild. Might have to do a little reverse engineering on the circuit board just to see what they're doing with the circuit. Because there's also another set of 2 diodes going across these 2 points, going through this big, huge X-rated capacitor, mains rated. And this is only a 650 volt capacitor right here, so it's not handling the rectified mains voltage. So that's very interesting how they got the circuit set up, because I don't see any. Oh, maybe they're filtering the mains through this big, huge capacitor right here. That'd be interesting. Let me do a reverse engineering on this and see. Okay, well, here's a schematic that I came up with for the circuit. Okay, let's take a look. So I've separated the circuit into multiple stages. So here's the rectification stage and power filtering stage, the battery charging circuit, and the relay circuit. And this circuit is just for the bottom part of the module, and not for the top part right here, which just contains the microcontroller and the display driver. So first, here's the rectification stage. There's a full bridge rectifier and a little X-rated capacitor that has a effective impedance of 2.65 kilo ohms. In series with 150 ohms means that it's 2.8 K of impedance between the live and neutral. Then it goes through the rectification. Then you get 25 volts out. I measured it with a multimeter, so I made sure it's 25 volts. There's a 100 microfarad capacitor, 105 degree rated, and it's 50 volt capacitor, so it's plenty of overhead. And then what I believe is a Zener diode just to provide better regulation of 25 volts. I think they're relying on the impedance between the live and neutral to pull this voltage down hard enough to get 25 volts out. Because usually, it'd be in hundreds of volts coming out of this diode bridge. So they must be relying on this impedance. And then there's just a 1 meg bleeder resistor on that big cap X-rated capacitor. So the battery charging circuit looks like this. There is a 6.8 K resistor, and then what I believe is another Zener diode to provide 1.9 volts of regulation. And that just goes through another diode just to bump it down to the battery voltage. And I measured 1.33 volts across the battery when it's charging. And then finally, we have the relay stage, which is a NPN transistor. Here's the relay right here, the relay coil, and then the switch. The switch goes right across the live input and the live output on the circuit. And it's kind of a unique way to drive this transistor right here. This pin goes to the microcontroller from pin C, And when this microcontroller pulls this pin low, it sucks all the current out, like essentially, because this is a Schottky diode, and this is just a regular diode, so the current would want to go through the lower path of resistance, going through the Schottky diode, making it so no current goes through the regular diode right there, or a very minimal amount. And when this pin goes high, it all goes through this diode, turning it on, and closing and making the relay energized, closing the switch. So, and this diode is just a recirculating diode to prevent the inductive kick that would destroy the transistor. And there's some sort of voltage sense going on, because there is a little circuit that goes to the microcontroller again, just to see, and this is on the output side, so maybe it checks to make sure it has closed the relay properly. So that's just a little look at the schematic of the circuit. There's a lot of taps going to the microcontroller. There's another tap right there that monitors the input voltage, I would think. And there's the plus and minus to the microcontroller, the power supply. There's one that turns on and off the NPN transistor, and there's one that monitors output voltage. This is a front panel microcontroller thing, and it's one little round circuit board. Looks like it's pretty nice. Okay, well, that's the connection right there that goes down to the power circuit board that I call it. And there's a little crystal right there, some capacitors, and the LCD display connections right up there. And it's a chip on board thing. There's just a black goop on there. And I can't see anything on that capacitor, any frequency norks on there, so it must be on the other side. And it is glued down, which is pretty nice. And here's the date code on there. It's 1348, so 2013, 48th week. That's pretty recent. Rojas, Underwriter Laboratory, Mark. This is fully certified for mains operation. Now let's take out those screws. Another just standard Phillips screws again. Okay, well, those are really cheap screws in there that I almost just stripped one out just trying to unscrew it. So I don't think I'll take it further apart. I don't think it's going to be too interesting on the other side, just because it's probably just a little, little push button switches right there. Maybe like through hole. Kind of feels like through hole switches, or just carbon contacts on the other side, and just a standard LCD display. So I hope you like this teardown of the Apollo 7 digital timer for turning on and off outlets at certain times. It looks like it works pretty good from the time I've had it. There's some talk about it not working after about 6 months, which might be the fault of the relay. The relay might need to be replaced with a nicer, higher quality relay after a certain amount of time. But that's easily done with the right equipment. And overall, it's not the worst build quality, I would think. The only problem is that the capacitor had dry solder joints on it, and I had to resolder them up. So that wasn't too good. That wouldn't be very good when it fails. That might have been also the problem why everyone was saying that it fails in 6 months, is because sometimes the capacitor would have the dry solder joints on it from their reflow process or wave soldering process. But all in all, seems like it's a pretty sturdy build, and yeah. So hope you like this episode, and I'll see you later.